today I'm going to speak about the BlackRay open source data engine. Just coming in. I assume most of you have not heard about it. It's a project that's been around, we've been developing on it since 1999. So it's had quite some history, but it's only been open source since 2009. And it's more of a special purpose kind of database. So the audience we receive is usually a lot smaller than, let's say, MySQL or MongoDB. So we want to talk what we call the state of the engine. And there are some topics I would like to talk about today. I hope it's technical enough for those of you technically inclined and shallow enough for those of you that have never heard about it. So let's look a little bit about the basic technology of BlackRay. First of all, why do we call it a data engine? Why don't we just call it a search engine or a database? And the reality is it's actually hybrid. It's a hybrid between a relational database and it incorporates a lot of the features we know from search engines. So we came up with this term called data engine. And you find us on Facebook. It's facebook.com/data engine. That's where we have our fan page. So, what do we have in the database? Well, it's fully relational. So you have the traditional instance, schema, tables. You can join between tables. We support columns and rows. So we are not a document store, but it's an actual database table. And we have SQL via JDBC, ODBC, and a lot of other drivers. But then we also have a lot of things we know from search engines. So we have full text. I know there's lots of databases that have full text support now, but when we started doing this in 1999, there was not a whole lot of full text search in databases. We do phonetic and approximation searches. You can have an alias search on a column, things like this. All things we typically associate with search engine, as we all have in Google. And we have very low latency. It's because it's an in-memory database. And that was one of the key aspects when we built it. Very low latency, high throughput. So it's always good to have a picture. On the very right-hand side, you see what we call the data universe. This is what BlackRay rotates around. It's resident in RAM, and we hold everything in what we call an index. Back then, we didn't really distinguish between index or table or whatever. We just called it an index. You access the data universe by means of an instance server. So it's a process that gets started. It's written in C++. It hooks up to the network. It allows you to query or perform operations against the data universe. And it supports transactions. So the data universe really is just a big object pool that organizes the data in a very efficient manner. The instance server is responsible for the commands, for the redo log, for transaction safety. We persist onto disk if we want to, so we can have recovery after a server restart or something. And we have a bunch of APIs. So actually we really come from the no SQL field. Back in 1999 we had no SQL, we had a bunch of APIs, actually C++ and Java. Nobody talked about Python or C# in 1999. But due to customer demand, we actually added SQL to it. So we have a new process running, that's a SQL to BlackRay translator, and this one mimics Postgres. So the protocol we speak here is Postgres. Here we speak the same protocol as the other APIs. And it all gets translated to the objects in our data universe. Inside the data universe we have 5 perspectives on the data. We have a dictionary index and a posting index, which is traditionally called a invert index. The third layer is a row index, where we actually hook up, where we actually associate the row ID with all the columns that belong to one row. And then we have 2 additional layers that you will not really find in a lot of databases. One is multi-token, which allows us to have multiple tokens in one column. And then we have a multi-value layer. And this allows us to store historic values for a column. So if you do an update, you can actually keep the old value in like a shadow of the current cell. And this allows you to query, for instance, old names. When we built this, it was built for a phone book. And one of the things with people is they change addresses and they change phone numbers and they change names. So if I'm looking for somebody, somebody who got married, they may still be in the phone book with the old name or with the new name. So it was quite important for us to keep track of historic versions of the data. Besides storing the data, we keep a lot of statistics in our index, mostly token frequencies and combined token frequencies. And they are very, very important for our optimizer to do quick searches. Like I said, we store everything in memory, so we have searchable and non-searchable columns, but everything gets stored in RAM, because as soon as you have to hit the disk for retrieving something, you're again bound to I/O. So here, we have two parameters that are important for the performance. It's the CPU throughput and memory bandwidth. We do something we call row-based storage bit compression. When you load data into BlackRay, it's all UTF-8. That's the only encoding we support at this point. But rather than storing variable length or UCS16 strings, we actually create a pseudo alphabet. We actually look at all the characters that occur in all the tokens. We build a new alphabet. And it turns out if we use traditional European languages search, we usually use a 6-bit alphabet. Because all the characters, A to Z, plus the numbers, plus the few extra characters we have in European languages, fit nicely into 64 values. So a 6-bit alphabet is really all we need for that purpose. Today, this is much less important than it was 10 years ago. Today, RAM is very cheap, and machines with big amounts of RAM are easily available. When we built this, we had the challenge to have a machine with only 4 gigs of RAM and fit in about 100 million records, people with phone numbers, and we actually had to squeeze out every single bit that we could to fit this into RAM. But even today, this still makes a lot of sense. If you have columns that have binary values, you really only use 1 bit in RAM for that. So if you have lots of flags, that's very, very efficient. Table versus index. In a traditional database, you have data in a table. Usually it has row IDs and then fixed or varying length columns. We actually have a set of index columns. They're either searchable or non-searchable, but we don't actually keep a copy of the data in RAM. A searchable column will get stored only in the normalized form. So when you want to retrieve the data, you will actually get the lowercase normalized version of the data. If you want to retrieve the data the way you stored it, you have to create an additional column that keep the data in its original form. So we don't really have the notion of a table in the data universe. We have our 5 layers of index data, but no real table that holds all the data. And one important thing is that only columns that are marked searchable can be used in a join. That's very important. A very important aspect of building BlackRay was wildcards. And the use case we had required wildcards in the front, in the middle, in the end, but not a combination of wildcards. Because at some point, or no random combination of wildcards. You have wildcard in the front and in the end, but not in the middle as well. So we use what we call a permutant index. Who of you has ever heard about that? It's the best publication we found is in the book on information retrieval from Stanford University Press. Was published in 2008. Actually 10 years after we built this. And the idea behind it is that we store rotated versions of the words. And if we want to perform a search for everything that starts with L, all we have to do is rotate the wildcard to the end, insert a $sign, and perform a binary search on the sorted list. Then once you've found the matches in this list, you use the second layer, which is supposed to index, to find the actual rows that contain the word. This is not the most space-efficient way of doing it, but it's the most performance-saving way of doing it. So we had a problem with the space inefficiency, and therefore we actually now use something called a compressed preterm index. There's a very nice publication on the ACM, and I think you don't even need a login to download it. This one saves about 80% of the space and costs almost no performance overhead. Essentially, you're folding in RAM, you're folding the lists into each other and just using pointers to point to it. We then use an additional layer in the index, which is the multi-token layer, to combine the different tokens in one column, so we can do true full-text search with wildcards. And you can keep the ordering of the tokens, or you can have random ordering of the tokens. You can specify which one has to be first, all without extra overhead in the search. When you do a multi-token search, let's say you have a text with 20 tokens and you're searching for five of these tokens, then we perform a lookup for each and every one of them. They could all have wildcards. And we figure out which is the smallest match. And from there on, we build the smallest possible cross product. That's significantly different from, let's say, how MySQL does it. MySQL will always take the first one, start with a set of row IDs, and then try to do a cross product. And sometimes, especially if you have lots of, like, let's say, 100 million documents in your database, very often the internal join size is too large. And so you end up with a result set that does not contain everything that you were searching. Okay. Now let's get back to the more basic things. Besides the focus on high performance and full text and our obsession with getting things done fast, we also built a few standard features into it. Initially this was a library, so you had to write a custom loader program for every use case that you have. And now we have an XML and a CSV loader, so you start up your instance, you put a CSV file somewhere, say load data, and we just load it. Loading is very fast in BlackRay. We don't touch the disk on loading besides reading the file. And we load about 20 gigs of data in about 30 minutes, including indexing and writing it back to disk. And this is done on a single CPU machine. After you load the data, you will take something we call a snapshot. And that's actually a serialization of the entire memory image of BlackRay. So there's no processing done, it just dumps out the string onto disk. You can compress it or not, depending on what you like. And this snapshot you can then copy somewhere else, and it's a complete backup of your data.
How do you do exactly the snapshot?
Sorry?
How do you do exactly the snapshot? I mean, is the database interpretable while you do the snapshot or not?
You can still read.
If you can't write?
No. During taking the snapshot, you cannot write. Not yet. This is something I'm going to talk about a little bit later. Initially, when this was built as a read cache only. Writing to it was done once a day, twice a day. And we had a shadow instance to write into, and then we switched instances. Then we implemented basic transaction support, but we don't have crash recovery during one transaction. We simply don't need it. We write a video log, we have a snapshot. If we crash during update, then our RAM is lost anyways. So we roll back to the last snapshot, reapply the transactions, and that was sufficient for all the use cases that we had. So now that you've gotten data into it, how do you get it back out? Right now, the most commonly used protocol is Postgres for accessing BlackRay. So we speak the Postgres protocol on the socket. You can hook up any Postgres driver that we tried, work out of the box. So we don't support the full Postgres SQL syntax, but we do support all the message types that Postgres has on the socket. So JDBC, ODBC work quite nicely. And then we have binary APIs, Java, C++, Python, also PHP and C#, although nobody in our team uses C# or PHP, so we don't really maintain it. But Python, C++, and Java, we maintain actively. The good thing about the native API is if you have an application that builds dynamic queries, depending on user input, this is very efficient. There is no parsing overhead, no building strings, no sending strings across the network. We use the ICE library for network communication. That's very, very high performance. So it's something in the most projects that we do where we have dynamic queries, we utilize the API. And if you have the need to have human readable queries, then we stick with Postgres. The SQL parser we have is built with two tools called Lemon and Quex. Anybody heard about them? Lemon or Quex or both?
Lemon.
Yeah. So Lemon is a replacement for Flex. The syntax is much more readable than Flex, and it supports Unicode, and it's part of SQLite. And what we like about the toolchain is it's just one file. So when you have to bootstrap your toolchain, it's very, very simple. Quex is then used to generate the tokenizer. It's written in C++. It was quite buggy when we started using it because we were the first ones to use it for very large grammar. But the guy who wrote it was very quick. We posted a bug at night, and then the next morning at 5, there was a new version, and we could work with it. That was quite interesting. So it's a combination that makes very, very efficient simple parsers, and it's the only reliable way of supporting Unicode at this point. Of course, you can patch the existing code with support Unicode, but it's not that true. So what we've done recently is we now support user-defined functions in SQL. We don't support subselects, and aggregates we support only halfway. That's quite buggy. And we switched our data definition language to our proprietary DDL to standard SQL. Well, it's pseudo-standard SQL because we support things that traditional SQL does not support. Creating dynamic functions on the index is something that is not standardized in SQL, so we have a subset of SQL 92 with some additions that we need for the data engine. User-defined functions. When we built the library BlackRay, we knew that there were quite a lot of use cases we could solve with it, but we didn't know all the aspects of the data that we were loading. So we needed a method to implement functions on the index that could be executed during the select or during the data update. The first function we implemented was a phonetic search. A phonetic search allows you to search for a phonetic approximation of a name. Let's say if someone's name in German is Meyer, there's about 10 ways of writing it, and just from saying it, you wouldn't know how to write it. So you would just, in our search, type in any way to write Meyer, and you would be able to find all the different ways it was spelled. And for this, we have a small function that normalizes. You could use soundex, for instance, or a little bit more advanced function that normalize the data on loading, and then normalize the query string and querying, and that's all you need. There's almost no overhead in the search. So user-defined functions is quite an efficient way of extending the functionality of BlackRay. We use user-defined functions also for aggregates, but the aggregates still are quite buggy. quite important thing is, in the beginning we had a few people writing functions and they said, oh, this is all working great. And then I restart the engine and all of a sudden my functions are working. And they wrote functions that maintain state in RAM. They used malloc, allocates some RAM. Then we would serialize everything out to disk. Of course, not the RAM that they were using. And then we restart the engine. Everything looks fine except for the state of their functions. So functions can maintain state, but only if you use a temporary table in RAM that's managed by the instance. Because otherwise, there's no connection between the data that you want to access now and the later states of the engine. So this is what the function looks like. All the built-in functions start with fx underscore, and user functions can have any name except for fx underscore. So this would allow you to search the name from the employee table where the phonetic match is Mike. Of course, Mike is not very exciting. There are not that many ways to write Mike. And this is the corresponding way to create the function. Of course, you also have to write the function in C++, but this is the way to load it into the engine. We are experimenting with an adapter to implement the functions from MySQL. The method signatures are very similar, so we are working on an adapter to see if we can have MySQL or PGSQL functions loaded dynamically. So user-defined functions are fully implemented, and all the originally built-in functions that were hard-coded are now user-defined functions. SQL support is well underway. There's one limitation, and that has to do with the nesting. You can actually say, let's say you have an alias function and a phonetic function. You can actually mix them. You say, okay, well, I want to build the phonetics of the alias. And that's something that our current parser cannot parse. Also considering you could have multiple columns in your function, and then it's quite tricky to explain it in SQL. And that's the part that's not yet fully implemented.
How the function use the index?
Internally, we create a separate column. So if you have a column name and a function column name, then we create a separate set of values for the functions. And that allows you to perform a search on the name or on the phonetic of the name, either way. And one way we were experimenting was with the virtual column names. But if you use virtual column names, then it's difficult to combine functions. And this is going to be in the 0.11 release. Now, back at the old days, we did updates once a day. So if you have a use case like a phone book, the phone book doesn't get updated immediately. People buy new phone numbers, and then at night they do one run on the update. And that was pretty much sufficient for most use cases. Other use cases like a catalog, if you have a web store, you don't add products every second. So for most use cases, bulk updates were okay. We started to support insert and delete, but unfortunately not via the same API as we do the queries. So we have one API that allows you to query, one API that allows you to insert and update, and you have to switch the engine from query mode into update mode, basically that blocking the reads, and then after the update you enable reads again. And this turned out to be not really ideal. So we've had a few clients that asked for true updates. So the first thing we did is we pulled together the different APIs. And this is quite a big task because they're written with different libraries and different threading models. Then we enabled that via SQL. And we rewrote the loading process to actually use the unified API. But quite a hassle because the different APIs were optimized for different use cases, and combining them was a rather big task. But we still had a problem with the locking. So we experimented with different types of locking. We moved the instance level lock to a table, and then from the table to the row. And then when we did updates, the locking overhead was very huge. The query was really quick, but obtaining all the locks, even if it's read-only mode, was more than 100% overhead in terms of the search times. So we looked at other databases, and we again looked to our friends from Postgres, and Postgres uses something called multi-version concurrency control. So the current approach that we are implementing in updating is also MVCC. MVCC works the following way. You have each transaction has a timestamp, and each row, or each column and row combination, also has a timestamp of its validity. So when you actually insert new data, you create a new version of the data with a new timestamp. No matter how long it takes, when you do a query, you apply the timestamp of the query to all the data you're looking for. So you only see the data that is below the current timestamp that you've seen. You don't see the non-committed updates yet. And then when a transaction commits, you say, okay, now we're live, all the timestamps get updated, and you have one current version of the data. This is not so trivial thing to do if you support an arbitrary number of versions in the future. So we currently support one actual version, one version in progress, one not committed version, and one update version. So we have 3 versions of the data, and this requires us to do something to serialize the updates. So when you do a lot of updates, we perform them one by one. We don't actually apply them all at the same time to the same table, but on each table we apply the updates serially. So this is very lightweight. There's no logging. You have a little size overhead in the index, especially for the timestamps and for the extra data. But compared to the logging, it's a much more performance-centric approach. Okay, where do we stand? We have a rather slow release cycle by some project standards, but this comes from us using this in commercial projects as well. So we take time to implement features, test them, deploy them in existing installations before we release new stuff. And the updating turned out to be significantly more complicated than we had anticipated. So our last release was December 2009. We were planning on May 1st release of 0.11, but it's more looking like it's going to be end of June, mid-July. So for the 0.11 release, we plan the variable function architecture. That's completely implemented. We want to make all the index functions available in SQL. That also means nested functions. Update insert via MVCC. That's pretty much done. And we've improved thread and memory management. So it's a little bit better to analyze this, and it doesn't take so long to figure out bottlenecks anymore. We have an admin console, which is a nice web-based GUI for it. It allows you to do queries and everything, update, manage the data. And it'll allow cluster node management if I ever get around to implementing that. So 0.12, we plan for February of 2012. Then we will support prepared statements, subselect, true aggregate functions, and we have a few potential memory leaks. They don't really appear to be a problem in reality, but we have test cases where we can create memory leaks, and so we have to switch everything to smart pointers. It's not that trivial, so we gave ourselves a few months to do that. Our midterm roadmap, we are looking at sharding and partitioning. It's quite easy to cluster BlackRay. It's built for clustering, for horizontal scalability, but we don't have a built-in sharding mechanism. So we've used some external tools, DB shards for instance, to do the sharding. It works quite well, but we don't have anything built into the engine, so that's something we're looking at midterm. Our snapshot currently is not portable from one version of the engine to the next. So if you upgrade the engine, you have to actually dump your data and reload it. So we are working on a portable snapshot format, one that you can actually take from, let's say, Linux and move it to Spark, Solaris. We are planning a performance analyzer similar to the MySQL performance tools. And we want to make the statistics available via GUI. Currently the engine has very extensive statistics, but they're accessible only via SNMP. There's no GUI for it, so you can use Nagios or MRTG or OpenNMS to do the performance monitoring. But it's a quite hacky way of doing it. So we want to have a nice little GUI for that. One thing we've been working on is using BlackRay as a storage backend for the OpenDS LDAP engine. And it works well for read only, but not for write. So this is something that we had in the back of our hands. May actually not survive. A few more things. Believe it or not, but we are like memcached. We don't really have a lot of security built into the engine. Again, this comes from being a in-process library, which evolved to an engine. And so security and access control was never a really big issue. So now we support basic authentication and you can lock users down to certain tables. But we keep the user list in a file just like Apache does. And so the idea was to externalize this, use SSL for all the connections. This is something we have a few students that are working on this as a thesis project, but it's not quite committed yet. People approached us to support something called the Windows platform, which I don't know so much about. And then, of course, we always take random features on the mailing list, or when people have really good ideas and come to me and say, BlackRay should also make coffee, then we think about it.
Yeah. Of course, having your solution available as storage engine from SQL, you will have all this coffee.
Yes, among other things. We've also been approached by Postgres to see if we can integrate with Postgres. So, but basically, the use and access control is very important. We know this, but just from the edge where we come from, this was never much of an issue. So let's talk a little bit about the people behind. There's 7 of us working on it, and it's pretty much a community effort. So all of us are doing projects and basically do this in our free time and spare time. Most of us devote about 20 hours a week on this. So it's, the velocity is slower than, let's say, if this was a commercial development, but we're still quite happy with it. We do 2 developer summits per year. And it's a distributed team, 2 of us in Germany, 1 in the US, 1 in India, 1 in England, 1 in Ukraine, and 1 in Portugal. So it's a nicely distributed team. Okay, now, what I want you to do next is, first of all, you can get the source code if you want it. It's available on our Subversion site, and of course in SourceForge. If you don't want to use all our bandwidth. The complete checker with all dependencies is about 1.5 gigs, so we appreciate it when people actually use the SourceForge downloads. Anybody can register and try it out, create tickets, post something in the wiki, post something in the knowledge base, discuss ideas on the mailing list. We are open to all feedback. And of course, if you feel like you have way too much free time and you really want to do something crazy, this is written in C++ and Boost with lots of templates. So it's quite tricky. It's a nightmare, but you know, when people that can't sleep at night and they want something to do, this is a really excellent user. So I encourage all of you, if you're really bored and you have nothing better to do, or you actually really like to do coding, check it out. We're always happy to sign on new developers. We've managed to sign on one developer per year. So if I find a new one this year, then I'm glad. Thank you for your time. And now it's open for questions.
Consider optimistic logging instead of low-based logging.
Yes, we have considered optimistic logging, but then we carried out a democratic vote on the mailing list, and the vote fell in favor to MVCC. We may revisit optimistic logging when we implement something called along the lines of partitioning and sharding.
It can simplify your struggle for rights, because then you don't need to support the multi-version actually.
Yeah, we're quite open to that. I have to say that because of most of the use cases we use this are heavily read optimized. We don't have a lot of experience with the distribution of the rights.
Yes,
so
optimistic logging will not interfere with your searches, only will increase the possibility of doing rights. And it will be up to the application to manage the failures with optimistic logs.
Yeah, it's definitely, like I said, we implemented the MVCC with a one non-committed version only, because it was rather easy to implement. And we look at the different methods in the future. And we will probably support different update methods. So we actually still support the old instance level lock, because this imposes the least performance if you ever want to not update the instance. If it's a true read-only instance, then we have no logging at all.
What is the internal data structure?
I'm sorry?
The internal data structure is a BlackRay list.
It's a list.
It's a list.
Yeah.
So when you have MVCC, you are always a done.
No. If you turn on the MVCC, we have that gets preloaded to maybe 95%. And in the worst case, we have to actually rebase the chunks. Like I said, we are still in, when it comes to the real-time updates, this is the first release we're supporting. So we will have a learning curve on how to optimize that.
Because you have a list, you have still a lot of pointers to read out.
Yes. But the list turns out to be quite efficient for most other operations. So. There was somebody else? If there are no more questions, thank you for your attendance. It was good to see you here.